All right, this time we're going to talk about how magnets and currents interact. Specifically how, well, we'll see. All right, here we have a relatively simple circuit, which is just really a wire that is currently disconnected, but can be connected to the terminals of this battery. But across the wire in this long straight segment here, someone has put a compass, which is currently pointing this way, meaning it's a misaligned, I guess meaning this is east, I guess. And let's see what happens when we connect the battery. All right, you can see that it has changed. That in fact it points this direction. It's deflected due to the current. One more time. Significantly, right? Not a little bit, but a lot. Then there's some back and forth a bit, but that's just inertia of the system. It was discovered in the early 1820s that the presence of a current in a circuit can deflect compass needles nearby. That implies that current generates a magnetic field. And that's going to be important for us. As might be expected, the shape of the field depends on the path of the current. So now we're going to explore the big book of current-induced magnetic fields. We're just going to look at a bunch of different kind of current geometries and see what kinds of fields come out. At first, we'll talk about the geometry of the field, and then later on we'll start talking actually about the field itself. So if we have a long straight wire, for instance here we have current coming out of the page that way, then we see with these magnetic filings that they align themselves in circles. So the magnetic field must be something like this. Now here I haven't proven the orientation of it yet, and we'll come back to how to do that. And we could put little compasses around to figure out what the field would look like, but it would have to be something we know is forming circles. So it would either be clockwise or anti-clockwise. And we'll talk later about which one which and how it depends on the direction of the current. If we have a circular loop of wire, so this is now a circle of wire that's pierced the page a little bit, then we can see that the filings do this kind of weird thing where they're lining up, bending through. So we get something like this flow. And most importantly for both of these things, notice that the field lines are circular. They go in circles, so you can see like here. And they are closed. They don't start and end anywhere. They are a complete loop. This is very different from electric fields, where we saw that electric field lines started on positives and ended on negatives and were never closed, right? They were never just loops. All right, a series of current loops that share a common axis, as illustrated over here. So this is something that's sort of loop, 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 loop stacked together, is a device called a solenoid. Solenoids are technologically important because just as capacitors constrain an electric field to be inside the capacitor, it will turn out that solenoids constrain their magnetic fields to be pretty close to internal to the solenoid. You can see here how much denser the field lines are between the solenoid as outside. And so mostly the field is in here and very little strength of it outside. All right, the field lines due to a permanent bar magnet are also circular. So if we track, say, this field line, it exits the magnet. It goes from north towards south, but then it re-enters and continues along until it closes the loop. This is presented at the moment without evidence, and of course you can't really carve open the magnet to see that, because every time you break open the magnet, you make smaller magnets. So this is a little bit weird, but true. They have to be circular. In fact, all magnetic field lines are circular. Why? Because there are no magnetic monopoles. The field lines would start and end on magnetic monopoles the way that electric field lines start and end on electric monopoles, which is what we call charges. But there are no singular magnetic charges, at least that have ever been seen. They are just undetected in the universe in which we live. That doesn't mean they don't exist, but it's kind of we're 200 years on and haven't found any, so we're starting to think that maybe they just don't exist. All right, let's look a little more closely on the long straight wire. Here we apply the first of many of what we'll call right-hand rules, abbreviated RHR, of course, which is to say put your right thumb in the direction of the current, wrap your fingers in the wire to indicate a circle, and your fingers are also indicating they're curling in the direction of the field lines. And of course you could rotate your hand all the way around this pole. You'd always get that circle. So around a long straight wire, the field lines are the directions given by your right hand when your thumb points in the direction of current. Very often we'll have fields or currents that are perpendicular to a particular plane where interesting things happen. In other words, we'll have maybe all the motions happening in the plane of the screen, but we'll have a magnetic field that is perpendicular to that, or maybe with a velocity which is perpendicular to that, or whatever. And since drawing three-dimensional isometric drawings is annoying and hard, we have a new convention. We say that vectors that go into the page have little x's, and currents into the page have little x's and circles, and vectors that come out of the page have little dots, or they have dots inside a circle. The purpose of the circle is what's called a protector. If you're just going to have one little X, you don't want it to get lost, or especially one little dot, so you emphasize it by protecting it. You can imagine that these are current lines. These are wires that are containing that. In both cases, the symbols are meant to evoke the idea of an arrow tip coming through the page, so somebody has fired an arrow from below, and it's just piercing into the page at you. Or it's been fired from you into the page, and the fletching, the little arrow, feathers on the back of the arrow, are just about to disappear into the page. Is that particularly clever? I don't know. It's, as always with mnemonics, it's probably most effective because it's a little bit silly. A right-hand rule works for current loops too. Your book has a little description of why you might imagine that to be true, which has the idea of, say, take your long straight wire and bend it, and at every point you talk, you'll still have that circular thing going around. All right. They've got both views here that you curl your fingers around, where the thumb is pointing out of the page at us because the current is out of the page, and we see we get that kind of field. And here on the other side going in, we see the field going the other way. Notice that they are both contributing to the center. Right. Near the fields, near the wires, of course, the wires look straighter as you get closer and closer to them, so it looks more and more like just circular fields. And it kind of flattens out here and threads through the center, but there's always going to be out here like some loop that would close onto it. All right, this little video illustrates the use of the right-hand rule for current loops. Here we have a power supply. It's going to run current through this loop, which will generate the magnetic field. Alright, as stuff goes, and then they demonstrate that the direction of the current controls the direction of the magnetic field. You'd pretty much expect that, of course. Now they're going to flip the direction. In case you didn't believe them, they want to show you for sure. And now they're going to move that compass around to get the magnetic field, which is clever and cute, but a little tedious. All right, remember that magnetic field points such that the compass points north around the field in the direction of the arrows. They only showed one of those loops, and hopefully you'll believe the others. And here's how you use right-hand rule to figure it out. The current is moving that way. At least that's what they're alleging with their thumb. You'd have to be able to see the ports here to be sure. And of course, since the solenoid is really just made of a bunch of coaxial loops, in fact, usually a lot of coaxial loops, the right-hand rule will work for it as well, as you'd expect. They do point out here the field has to be a lot stronger inside because every one of these circles, which are going way out into space and coming back, all have to cram together inside to fit inside the solenoid. And remember, it's a very important thing about the field theory that the field lines never cross. Because if the field lines cross, then that means the compass at that point would have two different directions that would point north, which makes no sense. So the field lines have to stay spaced, and if we're cramming all of these field lines into this tiny space, then they have to get a lot closer, but density of field lines is the field strength. And so as the lines squeeze together, they've got to make the field stronger. As they say here, it's reasonably uniform inside, close to the center of the solenoid, meaning both horizontally close to the center and vertically close to the center. It's extraordinarily uniform, but at the end you get the same kind of weird fringing that we saw with capacitors. All right, so a compass is placed above a long wire. When a large current is turned on in the direction shown, in what direction will that compass point? And I want to kind of indicate something here. These compasses are not in the field. They're not real. This is the compass that they're talking about, and they're saying it will match one of these four. All right, so here they've sketched the field over here by showing you guys right-hand rule, where the current is pointing this way, so the current wraps around this way. So we have this field. So at the point that the current is, the compass is located, we can see that the field is directly upward, and the magnet should align. Remember that the red part is the north magnet, and that's what should align with north end of the magnet, and that's what should align with the field. So we get D.